Hello, everyone. Okay. Let me just share the screen with you. Would you please just let me know if you can see the slides? Okay. Okay, I will just try to start with a few questions that I had some discussion with some of your colleagues after the last lecture, and I kind of understand some of the confusion on one part of last lecture, material. Let's go back to this important element here. So just to give an overview of like what we discussed last time, we said basically we have a system. Most of the time, engineer will be asked to design this system. So you have a certain function to create, or you are designing. And if you remember, we said we have three types of systems or three types of application. One application in, when you have like a low energy location, and then you have a high energy location, and you need to move the fluid from this low energy to the high energy. We call it the lifting application, or, the pump is used in this system to lift the fluid from this, low energy level to this high energy level. And then we said another application where we have the same level between the 2 points, and we talk about what we call the recirculation application, where we have, when we take the fluid from the tank and then we bring it to the same exact tank. So it's kind of like, the pump here is used to circulate fluid inside the system. Versus other application where there is already a difference in the energy in the direction of the flow, but this energy difference is not, pushing that much, fluid inside the system. So we put the pump there in order to post the flow, like you just increase the amount of flow rate in the system. So in all cases, we are designing this system by, looking at diameter of the piping, what will be the component added, valves, elbows, and all this, right? And then when we start talking about the pump, selection, we said, okay, we have to understand first what is the pump characteristics, right? And then we give two examples, one for a positive displacement pump and the other one for a centrifugal pump. Okay, some of the question came after the lecture about which one is better. Okay, there is nothing. Okay, there is no a better here. Okay, it's mainly related to the application where these pumps are used. So if you remember, in the positive displacement pump, we said, okay, we have a pump that is used mostly for a very high pressure applications, like, for example, hydraulic circuits. Okay, like, for example, these cranes, lifting devices, stuff like that. So we need a very high pressure in this case. One thing that we mentioned also for this type of pump, that is, because of the operation of the pump, because of the design of the pump, you might have some kind of, variable, flow rate at the exit. But if with a certain design, for example, like a gear pump or something, you might see this fluctuation become very minimal, right? But we are sure, every time we are running this pump at a certain RPM, we are 100% sure that the flow rate coming out of this pump is that much, right? Because the pump doesn't depend on the pressure. If you have any restriction in the system, the pump has to push the same fluids, right? So the flow rate has to be constant, and that's why the performance curve of the positive displacement pump is on a vertical line on the HQ curve, right? So the same kind of flow rate at a certain RPM, of course, right? You only have leakage when you have very high pressure, if you remember. Okay, so there is no there is no like which one is better to use, right? But for centrifugal pump, which is very commonly used for many applications, We also said, like, we have a limitation on these pressures. So the pressure at the, at the exit, can be controlled by a valve, or like, you don't have to all the time to have a flow coming out of the pump if you even close the valve completely at the exit. It doesn't mean that you are going to do this. It means that this type of pump operation is different from the positive displacement pump. And in this case, you are expecting this pump not to operate at a very high pressures. Okay, so those centrifugal pumps are mainly used for their capacity of the fluid flow, right? So that's why you will see most of the the pumping station for oil transportations are actually a centrifugal type of pumps. You see this wastewater distribution in cities are are using a certain type of hydrodynamic pump similar to the centrifugal pump. Same thing for water distribution as well, right? So in this case, yeah, we have like maybe high pressure, but also very high flow rates in this case. When we start talking about like this system or the pump, how we're gonna match the pump with the system, we said we're gonna develop something called the system curve. And the system curve, if you remember, we said, like, we're gonna plot this system curve with a pump curve and get the operating point where is the intersection between these two curves, right? So, and I mentioned that in order to develop this system curve, right? So we get, what we call it here in this case, like, the potential difference between these 2 points, the tank 1 and tank 2, or this is basically the energy, right? So the energy between point 1 and point 2, and it's always the delivery side, where the pump is delivering to, right? So the energy at this tank minus the energy level at the suction side. Okay, so this will be the difference, and we call this is kind of the static head that the pump needs to overcome, right? And then we said the other part here would be the losses in the system, and the losses in the system here can be friction plus eddy losses as well. Okay. When we solved this problem last time, and we talk about the Bernoulli equation here, when I said Bernoulli equation here, we didn't mean that you apply really Bernoulli equation between point 1 and point 2, because the pump is not there, right? You don't see a pump here, right? You don't see an H pump here, right? But it's just giving you the same idea here. This is the difference between the two energy, if we consider velocity and also if we consider the pressure. But this is basically, these two terms here is, this is the delivery side, and this is a suction side, which is the difference between these two will be the H static total, okay? Plus the losses equal to H of the system, okay? You can look at it from you can look at this in a different way. So you have a pump, you are gonna put it in the system, right? And this system has two main resistance, right? Like, one resistance is the head level between these two tanks, okay? So that's why you are considering this H static total, right? You want to overcome this, right? And H static total all the time, H delivery minus or the head at the delivery side minus the suction side. If this is 0, it's 0. If it's a positive, that means it's lifting. If it's negative, it will be posting, right? So it's going to be like, you will put it as a negative sign in this equation. But the other resistance is to push the fluid in the system, right? So in order to push the fluid inside the system, you have to overcome the total losses. That's why we are adding, H static total here. And this is H static total plus the losses in the system. It just happened for this problem that we don't have any eddy losses, and that's why we only deal with the friction losses. To open tanks, no, not really. It's like, Trevor, like, you have to really think about energy at point 1 and energy at point 2, right? In general case, like we represent in most of these problems, tanks and tank here and tank there, but it doesn't mean it has to be a tank, right? It could be a point that has pressure and velocity and Z, right? So you are kind of, considering this total energy is your first level of energy, okay? Normally, when we are putting a tank here, it doesn't mean it is really a tank, right? But in many applications, we have a reservoir that is carrying fluid from one point to another point. You will end up with, in most of the cases with tanks, like, a reservoir or an area where you are, taking fluid from, like if it's a lake or like a river or like, right? Or if it's an oil tank reservoir, which like for oil transportation, you start having, those tanks that has the crude oil, and then you are kind of, taking this oil through pipeline from this tank to the tank in the ship, for example, for export and so on, right? But in general, you just deal with energy at the first point in the system and the energy at the last point in the system. Okay, so this is just, sorry, just I talk too much about this, but this Bernoulli equation here is not really similar Bernoulli equation when you are putting like energy between 1 and 2, right? This Bernoulli equation here to determine the system curve. For the people are like to remember, equations, the system curve is always H static plus losses, right? So if you want to ignore all these small little details, at the end, H system will be the H static total and plus the losses. And H static total here has to be all the time is a delivery side minus the, the suction side energy. Okay. So we spent time talking about this, and I hope you guys, if you solve the problem yourself, you might, with some accuracy, getting those numbers from these, from this chart here. So there's going to be some kind of variation based on your very accurate way of determining those points on the map, but it's going to be within a certain range for sure. And then we went to another important, extremely important topic that we talk about at the end of the lecture last time. It's called net positive suction head. So we said we have another curve, and this curve is a manufactured curve. It's another characteristic of the pump that is always, we put it there, right, on the chart of the pump, and is representing the net positive suction head, required, by this pump, right? And we mentioned that this kind of net positive suction head is very important to evaluate, because if you don't really consider this in your system, or like, the location of the pump inside the system, you might end up with reducing the pressure at the suction side of the pump. What is this, reduction of the pressure will create is going to create what we call it the cavitation problem, right? So, and then we said, okay, this net positive suction head available by the system, or, it's the pressure atmospheric, because vapor pressure is an absolute term, right? So all the pressure of the vapor pressure for any fluid listed in any property table is basically absolute, right? So that's why we are considering the pressure atmospheric here is a value for the fluid pressure in this case. So we are putting atmospheric condition here using the absolute scale, right? Z here is the location of the pump, okay? And then losses in the suction or the inlet sides, okay, minus B vapor, because here okay, and maybe I can elaborate more on this here. You have a pump, you have a tank, and this level here, and then you have a pump here, and this pump is delivering the fluid into another part of the system, right? Don't even worry about this side here, okay? We only worry about this side here for cavitation. Why? Because this is the location. This is a location. This is a suction side. This is a location where we can expect a reduction of the pressure. Remember, like, when we draw the centrifugal pump, right? So we did it like this, right? So the pump is basically rotating, right? So this is the RPM. So as the pump is rotating, this impeller is rotating, right? It's making a suction here. Remember, like, you know, how you swirl the fluid inside a cup in the bottom or in the middle, it's going to be some reduction of the level, but in this case, because this is closed system, is going to be a reduction of the pressure. So you have suction at we call it the eye of the pump, or the impeller eye, right? The inlet, and then the fluid will go like this. So the location here, this is a suction pressure, and this is a delivery pressure. Okay, the pump, the centrifugal pump, all the time is gonna like create like this additional energy that converted to a pressure energy at the exit. So the pressure at the delivery is gonna be high. It's gonna be higher than the atmospheric for sure. So it's not gonna be a problem for cavitation, right? The only problem for cavitation can happen in the suction side here. Okay, that's why we look at this line here is your reference point. So this is your reference line, and the pump location here, this pump location is Z of, we call it the Z inlet, or the Z of the inlet of the pump, right? So now the pressure here is atmospheric. Okay, so if you go from point A to point B, right? So pressure here is atmospheric, okay, minus whatever, like, the losses or the all energy difference between A and B, right? This is what is, so pressure A minus ZI minus losses between, the tank and the pump, right? Minus B vapor. Why minus B vapor? Because you want to make sure that this value still higher than what is required by the pump. Why is that? Because if the pressure reduced, what will happen in this case, liquid will evaporate, because the pressure or the pressure is keep reducing to reach a vapor pressure. So in this case, the value for the pressure at this location will be enough to evaporate the fluid. So the fluid will evaporate, bubble will so bubble will formulate, and then what happened in this case? This bubble will go in this direction, and what happened in this case? Okay, those bubble will see a pressure increase, and what will happen in this case? All the liquid or the vapor will condensate, and the liquid will jump into the cavity of this bubble, or where the bubble disappear. Okay, and if you remember in chapter 1, we talk about cavitation as a very serious issue that can happen in the centrifugal pump like that. Okay, so in order to avoid this cavitation, you have to make sure that this value, this total value of, we call it the net positive suction head, and this is available by the system, is greater than what is required by the pump. Okay, so the required by the pump is listed on, or charted on this chart here, right? So graphed in this chart. So what you need to do is like calculate this for the system and see the difference. If if this available net positive suction head is greater, that means there is no cavitation or possible cavitation. If it's less, that means you might see cavitation happen in this case. I don't know what forces mean here. So the pump is overcoming all the forces. I think we have to really adjust we are almost at the last week of the fluid mechanics. So we have to be more careful about what terms we use. Okay, so what forces here? I didn't mention any forces in this whole chapter. So you mean energy losses? Yeah, but okay, pressure. Okay, Forces, when we talk about forces as an engineer, okay, when we talk about the pump and forces, that mean it is related to the forces on the impeller, that is for design and material and, you know, the casing, welding, stuff like that, right? This is the forces. So, but when we talk about fluids, we're talking about the pressure energy. And this, you know, pressure energy here is it's related to the fluid, right? So you have to keep in mind that in the fluid mechanics, we are not really looking at the surface itself. We are not really looking at, you know, the material. Like, you know, if this pump material is stainless steel or is a cast iron, right? We are not really getting into the pressure distribution inside this thing. So here, the pump is required in order to, provide energy to the fluid that make the fluid move from point A to point B. Okay, so vacuum, there's no vacuum here, but there's something called vapor pressure. And this vapor pressure is a property of the fluid. Okay, so maybe we'll just continue the discussion I have here, and then I'll look at the, the questions maybe later. Okay, so in this case, we have those bubble here will collapse because the pressure here is increased, right? And what will happen in this case, you might see, fluid jumping into this cavity, and of course, is going to be happening all the way here, and that's why you will see lots of impingement, like those liquid is hitting, hitting this impeller case, and that's why when you look at a pump that is suffering a lot of cavitation, and you open the pump, you will see the impeller at the end, the exit part of the impeller, right? So if you look at this impeller here, so here you will see a lots of damages in this location here because of the cavitation happen, right? So net positive suction head is a very important criteria you have to keep in mind when you are dealing with a system design. So you have to make sure that your net positive suction head available in the system is greater than the net positive suction head required by the pump. Okay, and the main criteria here is to make sure that the whole pressure minus all the losses is still greater than the vapor pressure, right? Which means that you don't have a scenario of cavitation in this case. B vapor, if you remember, and if you remember the chapter 1, when you open the property charts for any fluid, you will see that this B vapor all the time is negative value, right? Negative value here in this case, because if you're looking at, I think maybe, I don't know if Cedar, if this is what you meant by vacuum in terms of the vapor pressure itself. Yes, if the vapor pressure is given as a negative value, that that this is actually given in the gauge term, right? Because gauge mean that atmospheric is 0, lower than the atmospheric is vacuum, higher than it's plus, right, or positive. But vapor pressure given in any property table will always given in positive value, which means that this B vapor given to you is an absolute term. It's an absolute scale, right? So, so just keep in mind this, okay? Let's solve a problem here just to give you an idea about like what is meant by considering the condition of the system in order to avoid cavitation of the pump. Most of the time as an engineer, you will basically look for a pump chart. Like you're gonna buy the pump from a certain manufacturer, you just go and search the catalog for all these pumps and try to match it with your system and find out all the properties. You just make sure that your system gonna run properly at the condition that you wanted, and also without any problem, which is in the pump domain, it's going to be only cavitation. This is where your main concern will be in this case. Okay, so I have a chart like this, and the chart is given for for this pump at the speed, different impeller. If you remember, we talked about this before. So you might have, this is actually a chart for 3 impellers, like a pump that if you use an impeller inside 20 inch, 28 inches, or 32 or 36 is going to be like, inside this pump. So it depends on which one. So this is 32-inch pump, which means that in this case, I will highlight this. So this is basically the pump that we're talking about here. So this is like, we have to really ignore the other two blue lines here because this is not part of this problem, right? So this only the 32-inch pump. And it is pumping 24,000 gallons per minute of water at 1170. This is the one here. So the condition that we are running here is 24,000. Okay. From a reservoir whose surface is at 14.7 pounds force per inch square, PSI, absolute. What do you mean the surface at 14.7 PSI or pound per square inch? This means the atmospheric condition is 14.7. So this tank or surface at this level, absolute mean, this is your atmospheric condition. So in this case, I have this is a pump, B atmospheric here is 14.7 pound per square inch. Sometime and this is in real industrial field, you will see it's PSI, mean pound per square inch, 14.7. Okay. And flow rate here is 24,000 gallons per minute. Okay. And this is a 32-inch diameter or impeller diameter pump. Okay. Okay. So, if the head loss from the reservoir to the pump inlet is 6 feet, so H losses between the tank to the pump is 6 feet. Okay, so this is basically H loss inlet. So we call this is inlet. So the inlet side here had the losses of 6 feet. So all the losses here, including everything, is 6 feet. Okay. Where we should put the pump inlet to be placed to avoid cavitation of water at 60 degrees Fahrenheit. Remember, the vapor pressure all the time is a property for the fluid. But if you remember, when you look at this property table for fluid, it is giving at a different temperature. So you can actually have the same liquid, but at different temperature, you might see a different vapor pressure value. And this is a property dependent on the temperature as well, right? So at 60 degrees Fahrenheit, B vapor is 20.26 pound per square inch. So B vapor is 0.26, pound per inch square. This is the same as PSI. Okay, and it's given here. You see here absolute, right? But even if it's not even mentioned absolute, that you know that this is an absolute, because 0.26 is a positive number, and we know that the B vapor always actually is lower than the atmospheric. Okay, and the specific gravity here is 1, which is basically water, right? So this is specific gravity here is 1. Okay, and he's asking you to find out where this pump is located from the level of this tank. So this is a Z location of this pump, right? So from this surface here to the pump, okay? So where is the pump is located? Far from the surface of this tank, okay? So it requires ZI, okay? To avoid okay, you're just trying to explain to you in the problem, but it's as an engineer, you shouldn't, know that it's the pump location is always dependent on avoiding a problem in the system, right? So, and this problem for the pump is cavitation, right? So you don't have to tell you to avoid cavitation. It's just like, it could be a question to you, like, where the pump should be placed. That's it, right? So you're gonna decide, okay, in order to avoid cavitation, the pump should be located based on the criteria of net positive suction head, right? So now, if I look at this, problem, and I know that this is running, the pump should be running at 24,000 gallons per minute. I don't have even a system here, right? I don't have to worry about that, right? The location, the pump point here, this is a pump operating point. This is 24,000 gallon. So the point on the system curve, the point on the pump curve is this point. Okay. Now, what can I do for the net positive suction head required by the pump? So at the 24,000 gallon per minute, if I extend this line here, this is a 24, right? So at this location here, this is basically the value for net positive suction head. So you see here, the scale for the net positive suction head is on the right side. So between 20 and 50 here. So if you look at this, this is your net positive suction head required by the pump. Okay. So the pump is basically, in order to operate without cavitation, you have this value for net positive suction head, right? At the same time, so let me just add this. To avoid cavitation, okay, the net positive suction head required by the pump has to be, or the available is 4 terms, right? The net positive suction head, let me just write it this way. Net positive suction head available by the system, which is the pressure atmospheric minus ZI minus H loss at the inlet minus B vapor over rho G, right? And this one here is from the pump chart. Okay. Yes, it's just like, net positive suction head required by the pump is manufactured, right? Is design. It is a design criteria. Okay, I cannot really say it is dependent only on the flow rate here, right? But how can you determine it from the chart? Yes, you determine it by looking into, which condition here, right? So you'll see here, the flow rates. So this Q flow rate, and then you go and find out, the value on this curve here, right? But this is a manufacturer, condition, depend on the design of the impeller, how the impeller looks like, and right. And this value here is a manufacturer provided information. Okay, that's not something that is a function of something else. This is a design given value. Okay, and it's much more complex than the system. This part here. Okay, this part here. Okay, so this is provided by the manufacturer. Same way as these curves, right? This blue curve of the what is the relation between the flow rate and the heads are based on the hydrodynamic design of the pump, right? So what is the relation between Q and H? This is all provided by the manufacturer based on modeling, design, and other things. Okay, but it's a very typical for centrifugal pump to look like this, like, you know, right? And the same thing, the net post-suction head required for centrifugal pump, always like something like that, right? So same shape, but the value itself dependent on the design itself. Okay. Now for this case, I have the net post-suction head required here. Okay. I actually have it here on my note as 36. So this value here is 36, right? B atmospheric for this specific case is given as 14.7. And remember, this is pounds per square inch. And it looks like this is a 36, this is feet, right? So we have to convert everything here in feet. So I can multiply by 144. Remember, the per inch square, inch is 1/12 feet. Inch square, so it's going to be 1/12 square, which is 1/144, and then inch is at the bottom. So that means in order to convert, you know, the pound force per square feet, they have to multiply by 144. So this term here is 14.7 times 144. So we're converting this into pound per square feet. And then rho G in the British system, this is gamma, right? Which is gamma water times 1, which is it's water in this case, right? So this is 64.4. Okay. So this is gamma water here. So gamma water for the British system is 64.4 minus ZI, which is I don't know, minus H loss in the suction side is given as 6 feet. This is 6 minus B vapor given in the problem as 0.26. This is 0.26 again times 144 divided by 64.4. Okay, I can just do this in a simpler way. So 14.7 minus 0.26, 144 divided by 64.4. I'm just getting this number here with this number. Minus 6 minus ZI, just rearranging things, right? I can take these and I put it there, and I can get this here, right? So in this case, I have ZI. The whole number here is 27.3. For the people who are checking my numbers, please don't take it as, you know, ultimate truth. Like if you have any small variation, let me know. And minus 36. So this whole thing here, when I calculate it, it is 27.3, and that's 36 on the other side. So ZI here will be minus 8.7, and this is feet. Huh? Okay. What is this telling you? Anyone? Any perspective here? So in order to avoid cavitation, this criteria has to be valid. That means the location of the pump has to be less or equal 8.7. So remember, location of the pump, this is 0, right? This is your 0. So minus 8.7 mean, can the pump be put upwards, above the tank? How? What do you mean? It has to be below the ground. Yeah, below that, ground. Okay. So let me see here. 8.7 below the free surface. Thank you, Spencer. Yeah. It's right because the reference here is your free surface. So in this case, the pump has to be put under the surface, 8.7. It can be even lower, right? Because you see here, equal or less, which mean equal or less of minus 8.7. So minus 10 is less. So you can even put the tank even lower, right? But can you put the tank at 8 feet? Sorry, can you put the pump at 8 feet from the surface? Why? Because now this criteria will be the opposite. That means the pressure, which is 14.7, reduced by losses of 6, reduced by some criteria of B vapor pressure, and the liquid now evaporates, right? Because the value will be closer in this case, right? So the equal value here is the minimum, right? But you can actually increase or decrease this location of the pump. Decrease mean here, you put the pump even more down, right? So the pump has to be located at least 8.7 feet below the tank free surface. Okay. I consider this is, so cavitation will happen if it's 8. Yeah, that's correct. And that's why sometimes you don't see a pump that is, and that's why, you have to choose a different kind of pump if cavitation will happen. Like, sometimes as an engineer, you have a certain condition for this tank. Imagine you are lifting from a well. So the well is down. So the level of the water is down. So now you want to put the pump up, right? So now you're going to put pipe going down and then you are sucking this fluid. So it has to be a different type of pump. Yes, it's not a centrifugal pump, hydrodynamic pump working differently. But for this very specific pump, you are kind of, you can even put the tank up above the water level. So you can put the pump even for, above the water level, and then you still don't have cavitation. So it's all depend on the design and the type of the pump, right? This very specific type of pump, this is your limitation for it. Okay, other pump will have different value for the net post-suction head, depend on its design and so on. Right, and that's why sometimes you are using what we call it submersible pump. You are actually bringing this pump and you just put it down under the well, like you just put it down under the water. So it's going to be a submersible pump in order to operate, because once it is above the water level, cavitation will happen, or even the pump will not start. We didn't even mention something about priming of the pump, because the pump will not operate once you put it there. So it has to have some kind of something called priming for this pump. Unfortunately, we don't have that much room in this course to expand on the pump design and pump other conditions, but this is the minimum information that you need to know as an engineer for selecting the pump. How you draw the system curve, how you put the system curve over the performance curve and getting the operating points, and making sure the pump can operate without any cavitation in this case. A well would use a positive displacement. No, not again, like, I'm not saying this is like has to be, but you have seen guys many times. There is something called like plunger pump. It's similar to the positive pump. The general idea here is to make sure that cavitation does not happen, or the pump can start by itself, right? So in this case, I agree with you that we can use a different type of pump. Positive displacement pump not all the time is a solution, right? So, but I agree with you that no cavitation. No, the pump in this case, you can still have cavitation in the positive displacement pump. as long as you are reducing the pressure, because when you are sucking the fluid, sucking mean like you are reducing the pressure at the inlet. So in this case, you still have a negative pressure. So not all the time you have, in the positive displacement pump, you still have suction. And in the suction action, you have negative pressure. So, but the value for net positive suction head required by the pump in the positive displacement is much better than the centrifugal pump. But again, I don't want to confuse you about these details. We are not really, or just scratching the surface of this. I mentioned to you a whole course that is only on pumps that can be, where people are interested to expand on this. The turbo machinery itself, it's a very exciting and very important element in any engineering field, because the pump is considered to be the heart of the whole society. Like, when you are kind of moving fluid around, the driving force here, pump, blower, compressor, all these equipment are, the driving machines inside these systems. So it is very important, engineer, to have at least minimum knowledge about dealing with these applications. I trust you guys, once you graduate and you're focusing more into the application or the job that you are working on, you're going to spend more time understanding more. But at least remember these kind of basic fundamentals. What is the system curve meaning? What is the cavitation means? What is the net positive suction head means, right? What the pump, what is the difference between the not positive displacement and the centrifugal pump in terms of the operating principles, right? And based on simple engineering sense, you will be able to figure out much more complicated related details about these applications. Yeah, yeah. Unfortunately, most of these basic courses like fluid mechanics and thermodynamics and all this cannot be as exciting as we want, because it's kind of cover very wide range of discussions. So I'm sure people are interested later on to expand on any of these topics, might find it very exciting, very interesting, right? So every part of these, these type of courses can be by itself a whole kind of, job and career for, for people. My plan not to start the new chapter today. My plan is to really finish this part of the material. I'm willing to, answer questions you guys have, but those are the main key important element in this chapter 11. One thing I want to mention before I forget is, because I've got some emails about the final exam contents, or next slide. Sorry. This one. So one questions was asked about the typical coverage for the final exam. We did cover the first 3 chapters in terms of problems, solutions in the midterm. Okay, just to make it easy for you, I don't think I will put any problem on these first 3 chapters, but it doesn't mean that I'm going to ignore these 3 chapters, right? Because viscosity, what is viscosity means, or how to get the vapor pressure, stuff like that is fundamental stuff, right? So there's nothing. You have to remember what is the pressure in terms of rho GH, or these kind of very simple fundamentals you have to really remember. But it's not going to be a very specific problem analysis or problem that you have to solve on the first 3 chapters, right? So so you can work on, starting from chapter 4, and I guess chapter 4 was a simple definition of fluid flow behavior, characterizing the flow. And then chapter 4 is a dimensional analysis. I don't remember, to be honest. But yeah, I mean, the problem analysis after the, after the midterm exam. So expecting to see some of these problems, and in addition to similar kind of format, like some of the multiple choice questions or true and false questions in the beginning. So focus more on this last part, and then try to, as much as if you are missing some of the fundamental that is needed, some information from the first chapters, you can just go and review it. The exam will be in person. To be honest, like, I think we have to move on to, because open book exam, it takes a lot of effort to create this course link, multiple versions, and yeah. I'm going to be in person. It's in person, yes. You have it already, I think, listed as one of the places in campus already, right? It's a assigned place by now. Okay. So that's related to the exam. The other part in the exam, people were asking about, like, formula sheet, or like, a cheat sheet, like, just like create your own, like a page, 2-side or something of whatever equation that you want to put there, or whatever information that you want to have, right? But please study for the exam, so you don't have to really learn stuff while you are solving the problem. It's just like, like put the, the information that you cannot stick it to your head, like, any equation or any relation. Graphs, I want to put graphs, fine. Just like, it's up to you. Space, just use it, whatever. Tables, and don't waste your time putting tables in this, right? Because if I have a problem that you need a table for, I will provide it in the, at the end of the exam papers, right? So I will put like this table over there. Make sense? Yes, I will. Yeah, sometimes it takes time for the stream to process that video, and I lost, I lost track, so I just forget about it completely once it's taking so much time. But I will do that, and I will also post these final slides with notes. Increasing the fluid level, having the pump lower. Yeah, because you have an available. Okay. Let me rephrase this thought a little bit differently. It's almost like the pump. Okay, if you have a lower, okay, if the pump is located here, and the level here is of the tank on the suction side, so this is available head. This is available positive pressure. Agree with me? If you have a head of a tank before the pump, this is available positive head, right? Now, by the time you are going to the pump, you are losing energy because of losses and because of the velocity and all this, right? So which means that the more head available before the pump, the less likely the pressure here will be negative. Can you see it this way? So the lower the available energy, right? The lower the lower the available energy, that means possibility of having a negative pressure at the inlet of the pump will be more. That's why the net positive suction head available by the system, which is this equation. So this equation here, right, is talking about, like, this Z here. This Z here is basically the head available at the just before the pump. This is basically the head of the tank available by the, right? Which means that this value here has to be, somehow is, making sure that the pressure is not reduced so much to at the inlet of the pump. I'm trying to. That's correct, Trevor. That's correct. That's why. But again, you're thinking about it this way, but now you have, when you formulate it, it's going to be like what? It's minus the losses as well, right? Because energy is reducing until come to the pump, right? So you got it exactly right here. Aiden, location of the final should be there, right? I'm guessing it should be online, like, you know, it is, I think it's organized by the central administration, so it is not there. Okay, let me check with the people in the school, because I receive, but maybe they're gonna post it soon or something. Yeah, because I received, like, you know, confirmation about the location. So I remember it is at 8:30 in the morning, and yeah, I don't remember the location. So just please wait until it's posted, but it is face-to-face, because some people now, they were wondering about switching their final exam into online. And we have the option to do this, but I don't think it's going to be helpful. So it's easier, because every time you have this hassle of submissions and creating multiple versions of the exam. I'm not sure. Positive cases in contact with, yeah, a lot of people are in contact with positive, you know, I don't know. Let me stop recording here so we can talk more about whatever you guys, if you have any questions, stop recording.